All right, so now that we have a general idea of what we're talking about with shielding, we can now go back and think about why it is that the orbitals are ordered in the order that they are. We know that the orbitals for multi-electron atoms depend both on n and on L, but we haven't yet addressed why, for example, a 2s orbital is lower in energy than the 2p orbital, or why, for example, a 3s orbital is lower in energy than a 3p, which in turn is lower than a 3d orbital. So let's think about shielding in trying to answer why, in fact, it's those s orbitals that are the lowest in energy. And when we make these comparisons, one thing I want to point out is that we need to keep the constant principal quantum number constant. So we're talking about a certain state. So we could talk about the n equals 2 state or the n equals 3 state. And when we're talking about orbitals in the same state, what we find is that orbitals that have lower values of L can actually penetrate closer to the nucleus. This is an idea we introduced on Wednesday when we were looking at the radio probability distributions of p orbitals versus s orbitals versus d orbitals. But now it's going to make more sense because in that case we were just talking about single electron atoms, and now we're talking about a case where we actually can see shielding. So what is actually going to matter is how closely that electron can penetrate to the nucleus. And what I mean by penetrate to the nucleus is there probability density a decent amount that's very close to the nucleus? So if we superimpose, for example, the 2s radio probability distribution over the 2p, what we see is there's this little bit of probability density in the 2s, but it is significant, and that's closer to the nucleus than it is for the 2p. And remember, this is in complete opposition to what we call the size of the orbitals, because we know that the 2p is actually a smaller orbital. For example, when we're talking about radio probability distributions, the most probable radius is closer into the nucleus than it is for the s orbital. But what's important is not where that most probable radius is when we're talking about the z effective it feels. What's more important is how close the electron actually can get to the nucleus. And for the s electron, since it can get closer, what we're going to see is that s electrons are actually less shielded than the corresponding p electrons. They're less shielded because they're closer to the nucleus. They feel a greater z effective. We can see the same thing when we compare p electrons to d electrons, or p and d orbitals. I've drawn the 3p and the 3d orbital here, and again what you can see is that the p electrons are going to be able to penetrate closer to the nucleus because of the fact that there's this bit of probability density that's insignificantly closer to the nucleus than it is for the 3d orbital. And if we go ahead and superimpose the 3s on top of the 3p, you can see that the 3s actually has some bit of probability density that gets even closer to the nucleus than the 3p did. So that's where that trend comes from, where the s orbital is lower than the p orbital, which is lower than the d orbital.